All right. Well, I'd say we go ahead and get started here. We've got a lot of great content. So first, I want to thank everybody for joining today. We know time's valuable. COVID's obviously made it tough for us to stay in front of our loyal friends and family members of the Interface family. And we'll be employing several of these webinars through the first quarter of 21 to ensure that we stay in touch with you. So things are muted, so we will encourage you to please use the chat. Today's topic is going to be on load cell basics. We get the most interest around our 101 entry level information blast that we send out, and thus we decided we'd start here. This is going to be the first, like I said, of several other monthly webinars with different content in each one. And again, we thank you for taking time to join. We hope you get some good information out of this. And most importantly, trigger some thoughts, some questions that you can then follow up with the team, either here in the Q&A or of course, follow up with us afterwards. So we've got Keith Skidmore, who's going to be doing most of the presenting today. Keith, not sure what that is. I'm getting messages. Keith is one of our most experienced team members, and he's going to be going through several different items. Keith, if you can go ahead and slide forward to the agenda, please. All right, so we're going to cover a lot of the basics, but I think even some of you more experienced users will get something out of this today. We're going to be load cell design, how load cells work, and then various aspects of how to ensure you're choosing the right load cell, and then things that factor into performance and the usability in terms of getting the best results out of the sensors through use. We'll have a few use cases at the end, and then of course open things up for an FAQ, where we hope you'll contribute questions through chat, and we'll do the best we can to address them here. So again, we got a lot of great content, so I'd like to hand it over to Keith and let him get started here.
Well, welcome everybody. We're going to talk about all of our favorite topics, load cells, and as Brian mentioned, there's a lot of material here. Some of it will be a brief overview. I'll be moving rather quickly, but we hope that some of this plants seeds for further conversations, and our application engineers are standing by with the ability to dive deeper into any applications you have or any questions on any of this we want to discuss in more detail. So to get started, load cell design and how they work. Some of you may know how a load cell works, some may not, but basically a load cell is a spring element, typically made out of metal. There are strain gauges mounted on the metal in such a way that when the load is applied to the load cell, the metal stretches a little bit. These strain gauges change resistance, and that's a repeatable effect. So a certain amount of load, a certain amount of strain into the strain gauges, a certain amount of signal comes out. And so moving on, the strain gauges are basically variable resistors. They're glued to the surface, and they say stretch or compress as the surface deforms. They're wired in a Wheatstone bridge configuration. What that does is it allows you to apply a voltage across the bridge and then get a signal output from the bridge. And the signal is in millivolts per volt, so millivolts out per volt of excitation. And it's really measuring deflection in the system using strain gauges. It's quite nice, very repeatable, and it's a method that's been used for many years very successfully. Capacities, models, and how to choose the right load cell. It can be a bit intimidating if you look at a catalog or our website. There's hundreds of different models. What is the difference? And certainly new people to load cells might really struggle with, okay, what's exactly the right one? I have to pick the right one of these hundreds of versions. Well, it may be that 50 of them could work. It's not always a single solution, but some considerations may drive you in one direction or another. You've got lots of different types. You've got pancake styles, you have tension and compression. You got compression only. You have S-shaped ones. Some are fatigue rated. Some are quite small. Some are little load buttons, literally like a shirt button. You have certain types of measurement, either shear beam or bending beam. That has to do with how the metal is deformed under load. You got rod end, canister load cells. Rod ends go on the end of threaded rods, for example. Load washers have through holes. You're going to be doing calibration work. Any intrinsically safe or explosion proof requirements. Your downhole for oil field use. Gigantic load cells for high capacity. So all kinds of considerations. A lot of times when you start to look at certain of these things, you can start to narrow it down to what load cell is, right? Like if you don't need explosion proof, obviously don't consider any of those load cells. Interface makes load cells from very low capacity down below an ounce all the way up to millions of pounds. And for those of you who work in the metric system, that's from the low grams all the way up to 15 meganewtons. The accuracy can be as high as 0.02%, which is quite good. The signals, as we discussed earlier, are millivolts per volt inherently, but we can provide amplification for 4 to 20 milliamps or 10 volts, whatever you may require. We also have digital output, so USB or Ethernet, we can accommodate all different kinds of signal levels. Some load cells want to be sealed if it's going to be outdoors or submerged under the ocean, for example. Sometimes it's subjected to high temperatures, so that's definitely worth mentioning when you're talking to an application engineer. It's going to be just in a lab at room temperature, or there'll be extended temperature ranges involved. Multiple bridges, those can be used for redundancy. We also have multi-axis load cells that have different bridges for each axis. Again, submersible, overload protection, TEDs. We do offer a lot of load cells with mechanical overload protection. We'll talk a little bit about overload later, but overload protection can be an important consideration. TEDs is a calibration method where the calibration data is stored on a chip. We can do that. We can do all kinds of special electrical connections and cables. You can do special calibration certificates with special runs, points, percentages of capacity. We can do proof loading. All kinds of things are possible. Interface. We make our own strain gauges. I mentioned strain gauges earlier. That's the core component of the load cell. One of the things that's unique about Interface is we do make our own strain gauges. They're a little higher gauge factor than ones commercially available on the market. It doesn't, we make our own, so we have control of the strain gauges, so they're very consistent from lot to lot. If you're buying strain gauges, there's a lot more variation every time you get a batch. They may be slightly different from the previous. So when we fine tune a design, specific load cell design, specific gauge, we can be sure we get that same exact gauge every time when we make that load cell. Higher gauge factor gives us a higher signal to noise ratio for higher resolution, which is important in some applications. We also get better fatigue life. Choosing the load cell, we have mechanical considerations about, is it threaded? You have physical limitations as far as size. It's also electrical, what do you have as far as a signal? What are you going to read the signal with? What supply voltages do you have available? Environmental, again, temperature, moisture, it's going to be outdoors, under the ocean, in an oven, those things are important. And then performance, what's your target? Are you trying to measure, within 1 pound, within 10 pounds? It's good to know what you're trying to achieve, then we can help, adjust or tune the system so that you get the results you expect. Talk about capacity. That's usually the first thing that people talk about when they say they want a load cell. Usually people have a pretty good idea of what load cell they might need if it's 100 pounds or 10,000 pounds. You have to be careful though, because you have to survive any accidental damage or any sort of strange behavior in the system. So say an actuator locks up or something happens unexpected, you want to be able to survive it. So you have to pick a load cell that's high enough capacity to survive everything that it might see. Also has to be low enough capacity so that it can measure accurately enough for the application. So say you have a 1,000-pound load cell. It may not be the best load cell if you try to measure 10 pounds, but if you also know that sometimes accidentally the system goes up to 1,500 pounds, well, that may be the load cell you need to survive that application. Now, you could also consider something with overload protection, which allows you to get a smaller load cell, say 100 pounds, but it's protected for those occasional spikes way above that. One thing to note, there's a safe overload range available in load cells on the specification sheets. It's called safe overload, and that's a range above the capacity, usually 50%, sometimes more. And that is where you're allowed to go, but you should try not to, and it's just for accidental use, basically. And repeated use up in the safe overload range will limit the life of the load cell. And anything beyond that, you risk permanent irreparable damage. So we talked about it being a spring element. If you stretch it too far, it doesn't spring back, basically. So if you apply too much load, when you remove the load, you have a permanent shift. That's damage. It can't be repaired. It can be re-zeroed electrically, but in the end, the metal has yielded. So at some point, they still may be usable, but you're starting to look at having to replace your load cell if that's happened. Mechanical mounting, one of the more critical aspects, how do you attach to the load cells? Will it be threaded? Are you going to compress and just press up against the surface? Will there be actuators or rod end bearings or clevises? Is it mounted to a plate? What is the geometry system? How much bending and what's the stiffness of the components? All those things are important and can affect the accuracy of the measurement. Load cells always have a live end and a dead end. This S cell here to the right is a good example where you can see where the strain gauges are in the middle. You have the dead end and the live end. The cable is attached to the dead end. And a good example would be, say, if you're trying to weigh something and this load cell is mounted to the ceiling. If you have the dead end mounted up, the cable weight does not affect the measurement. So if the cable were swinging around or somebody were to step on it, it wouldn't make any difference to the measurement. You might pull the cable out, but that's another story. If you mount it the other way with the live end up, then the cable would be part of the measurement. And if it swung around or somebody pulled on it, you'd see it in the measurement. So that's one of the good reasons to pay attention to live end versus dead end. Another thing this load cell is a good example of is if you want to apply torque when you install fasteners. You can see if you installed, say, a bolt into the dead end, if you held it by the live end, you'd actually be twisting it. And that twisting would be seen in the strain gauge area, and it could be damaging. So you always want to hold the load cell at the same end where you're installing a fixture. So if you're going to screw something into the dead end, you want to hold the dead end, say with a wrench or your hands, and vice versa. More mechanical mounting considerations. When you have a threaded connection, you want the thread engagement to be tight and preloaded if possible. And by preload, what we mean, if it's, for example, a 1,000-pound load cell, we might pull 1,000 pounds or more, maybe 1,200 pounds on the rod, and then tighten the jam nut finger tight. And when you let everything go, the threads are locked together. And that's good for a couple things. It takes the slop out of the system so you don't get any wear. It also helps reproduce our calibration results more accurately because that's how we calibrate the load cells. And for fatigue use, it's super important that the loads aren't sloppy, or the threads, aren't sloppy because it will wear out. For compression loading, you want one flat surface and one radius. Typically, the load cell will have the radius, so you want to load it against a flat surface. If you have two flat surfaces, you don't really know where the load point is. It may be in the middle, maybe towards the edges. If you have two radiuses, they'll tend to slide apart from each other and create bending, and it can be dangerous, actually, if the load cell shoots out under load. Mating surface interface low profile load cells are sold with or without bases, but they're mounted to a base, then the base provides an appropriate mounting surface. If you're using a load cell without a base, it's important that it be mounted to something that's similar to our base. And the bases are quite flat. They're also thick and stiff enough so they don't deform under load. You can get your most accurate measurement that way. So for example, if you had a load cell without a base and you mount it to a thin plate, as you load, the plate will bend and it'll distort your measurements. It may bring off-axis loads and bending into the load cell. And so, rule of thumb, the load cell base, or what you mount it to, should be at least as thick as the bases that we use. Should be similar material. If the load cell is steel, it should have a steel base or steel mounting plate. Aluminum, same. It also should be torqued to spec, just like a lug nuts on your car. If you were to torque them down, you'd follow a star pattern and maybe increment the torque up as you fasten. Next slide. As I talked about, with say mounting to a thin plate, or if you're in a system where there may be some deflection, you can get bending, or misalignment can cause bending. You need to consider that, and that's a lot. It has a lot to do with mounting and how you mount the sensor. We're trying to avoid bending moments, torque, or side loading into the system. Those can be damaging. They can also cause errors in your measurement, so need to be considered. Fatigue applications are interesting. We have fatigue rated load cells that are rated for hundreds of millions of cycles that are fully reversed. Some cases you need that, in some cases you don't. If you're going to cycle at 1,000 cycles during a test, maybe a fatigue cycle or a fatigue rated load cell isn't required. If you're looking for, long-term high frequency testing, probably a fatigue rated load cell is required. So when we want to discuss fatigue rating, we really need to talk about, what is the expected load profile? Is it tension, compression, or both? What's the magnitude of the loads? What number of cycles? We can start to decide, does it really need to be fatigue rated? maybe you need even a bigger fatigue rated load cell than you might think, depending on these loads. So it's important to dig deep in and figure out exactly what the loading conditions are, the expected life cycle of the testing, and your accuracy and performance requirements. Certain load cells are better for fatigue cycling than others. Typically, a stiffer load cell is better, less deflection means you get less strain, longer life. Interface low profile, shear beam design load cells offer excellent fatigue resistance. Electrical signal, again, as I mentioned, load cells have millivolt per volt outputs inherently. Those may be great if you have instrumentation that works with millivolts per volt. If you have a 10 volt input into your system, well, maybe you want a 10 volt output from the load cell. We can supply internally amplified load cells or inline amplifiers. So the important thing is to match the signal to your instrumentation. And we can talk about that a little bit later as well, but there's no necessarily right or wrong. 10 volts isn't better than 5 volts. It's just if your input is 10, maybe you want to use 10 volt input. If it's 5, well, 10 would be too much and you wouldn't be able to read to the capacity of the load cell. Noise immunity, some of the signals are more noise immune than others. 4 to 20 milliamp is preferred in very noisy environments with long cable runs, for example. And grounding is important, especially with amplified signals. And also with millivolt per volts with low level signals. You can get ground loops, you can get noise into the signal. So proper grounding is important. Environment, temperature considerations are very important. Within a certain degree, we can compensate for temperature or manufacture load cells that have special high temperature characteristics. For example, you can see here the limits are about 500 degrees for millivolt per volt outputs. Amplifiers, the electronics typically don't like as high a temperature, so 225. Temperature, can damage or fail the load cell. Can also cause errors. Again, if you have temperature cycling or swinging during a test, that can influence the measurement accuracy. So it's good to understand what temperatures are being encountered during the test, and we can certainly help you take steps to mitigate issues related to that if we know about it. Load cells can be in an oven, for example. It's very important for us to know that. We're trying to discuss with you, what the appropriate load cell is. Moisture and humidity. Some load cells are unsealed and they're not particularly appropriate for, say, outdoor use or somewhere where they might get splashed. Other load cells are fully hermetically sealed, welded, stainless. And those ones in some cases could be submerged, for extended periods in corrosive liquids. So a wide variety. The unsealed ones tend to be smaller and less expensive, and sometimes more accuracy can be had out of an unsealed load cell because the sealing can create parallel load paths. So the unsealed load cells can be the best choice in many cases, but we need to understand if there's other mitigating factors that might drive it to need to be sealed. Again, moisture, humidity, corrosives, those kind of things. Factors that impact sensor accuracy. The specifications are one, and load cells always have specification sheets, interfaces, full specifications on every product. Calibration of the load cell, cabling, what instrumentation you're using, and also mounting, as we discussed earlier. So specifications, each data sheet will have a list of specifications. You'll notice they typically don't have anything called accuracy. Up here it says accuracy, but it's actually a table of a bunch of different specifications. So you can't necessarily pick any single one of these to determine what the accuracy of your measurement is going to be. On the other hand, in many cases, you don't have to include all of these. Some measurements don't have some of these components contributing to their error, so you can ignore them. So again, discussing with your application engineer, talk about exactly what you're trying to achieve. We can kind of hone in on what specifications are most important and what we need to do to help make sure you make the best measurement. When you look at specifications, one thing you'll notice is they have different units. Sometimes they're percent of full scale, which is basically the calibrated range or the range over which you're using a load cell. Percent rated output is a percentage of the output or of the output at capacity. And so say 100-pound load cell, it's a percentage of 100 pounds. Whereas, you can also calibrate that load cell to 50 pounds and a spec that's a percentage of full scale, you could reduce the errors by that calibration. But an error that's percent of rated output, it's a fixed percentage of the capacity. Percent is a percent of reading. So if you're loading it with 10 pounds, it's a percent of the 10 pounds. If you're loading it at 1,000 pounds, it's a percent of 1,000 pounds. Some are percent per degree, which are the temperature related specs, and then some specs are time related. Linearity and hysteresis are very common ones. When you load a load cell, the signal outputs linearly with load, basically, but it's not perfectly linear. It actually follows a bit of a curve. And so linearity specification is how much curve is there versus a straight line. And that's the linearity. Hysteresis, well, the load cell follows a curve on the way back too. So when you unload it, it follows a curve, and it doesn't follow exactly the same curve as it did on the way up. And so hysteresis is the difference between the curve on the way up and the way down. And so this is a good example of a spec that you may not care about, right? So hysteresis error, if you're not going to be taking descending points, you can completely ignore hysteresis as your error. If you're just taking, 0, 50, 100% loads and you're done, who cares what the hysteresis is? Now, if you're coming back and trying to measure 50 pounds on the way down and want to see what the difference is, say, between coming down and up, well, the load cell hysteresis error actually contributes to whether you can actually, say, compare those two measurements. Their percentage of full scale, so special calibrations can improve and reduce the errors due to these specifications. We also have static error band, which basically takes into effect nonlinearity and hysteresis and non-return to zero. And if you fit a best fit straight line through the data and fit a band above and below that line, encompassing all of the data, that's your static error band. And then the static error band output is the output at capacity on that straight line. And so a lot of our load cells, we publish a static error band on the calibration certificate and a static error band output. And we would suggest that you use that when scaling the instrumentation. Non-repeatability is an interesting specification. It's defined as a maximum difference between output readings under repeated loadings, under identical loading, and under environmental conditions. And that's very important because in practice, it's actually quite difficult to achieve exactly identical conditions. So the non-repeatability effects can be quite good in a load cell or in the system, but it's really assuming everything is exactly identical every time you load it. And that's usually not the case. So a lot of times there can be significantly more errors than you might expect than just looking at the non-repeatability error. And that's a percentage of rated output, so percentage of the capacity of the load cell. Calibration. Calibration always has an uncertainty. Doesn't matter how great a load cell is, if you apply a poor calibration to it, you're going to have errors related to that calibration. You take a great load cell and miscalibrate it and get bad results. And the uncertainty of the calibration has to do with, how certain are we of the loads applied. So we say we put 1,000 pounds on it. Was it really 1,000 pounds or was it 1,010 pounds? And so those are published on the calibration certificates. And that's basically, what is the uncertainty level of the applied load? You can do special points. If you're going to be using a load cell at 30% of its capacity mostly, and you're really interested in measurements around there, we could calibrate it to 30%, for example. You could take extra points down in that area. A lot of things can be done that would potentially improve the measurement if we know that that's what is required. Again, calibrate as used in the application. You have some funny fixtures, or if you're doing something kind of unique, it might make sense to try and calibrate it in situ instead of having the load cell calibrated independently, because the mechanical connections can have an impact. And so you can kind of calibrate those out if you do it right. Something called an E74 calibration, which is per ASTM, and it's multi-run calibration, usually used for calibration. Load cells are used to calibrate other load cells or machines. There'd be multiple runs, taking many points and then averaging the points, fitting a coefficient curve to those points. Going on to cable length. When the load cell is manufactured with a certain cable length, that cable length is taken into account during calibration. If you want to change the cable length, particularly people like to add cables sometimes. So you take a load cell with, say, 10 feet of cable and you add another 100 feet of cable. That can cause significant errors because the cable resistance then creates a drop in signal. And you can calibrate that out if you apply a calibration with that new cable length. But if you're using the original calibration, you'll have a significant error. And again, it depends on the gauge of the wire. Thicker, fatter cable is better. You can see in this chart, the slope of the 28 gauge line is a lot more than, say, the slope of the 22 gauge and then even 16 gauge, which is kind of ridiculously fat wire, actually, but you can see that would be quite flat. There's something called sense, which would be a 6-wire connection. So if you measure what the excitation voltage is at the end of the cable, you can compensate that in your electronics. And then things like voltage and milliamp signals are typically not affected by, reasonable cable lengths. Instrumentation scaling, your measurement is only as good as your instrumentation. And so the instrument isn't reading correctly. It doesn't matter how good the load cell is. So how do you adjust the instrument? Well, you can actually apply a load to the load cell while it's attached to the instrument and scale the load cell accordingly. That's a good way to do things. You can also use the millivolt per volt output that's listed on the calibration certificate. And that can be done by, say, inputting that information into your instrument. And some instruments allow that and some do not. If you have an instrument that doesn't allow millivolt per volt input, you can use a millivolt per volt simulator. In that case, you would dial up a specific millivolts per volt and then tell the instrument that that's equal to, say, 100 pounds, and set your instrument up that way. Shunt calibration is similar to using a simulator. It's not as accurate, but it's where a shunt resistor output is listed on the CalCert, and then you can actually use that shunt resistor to induce an output signal that you can use to scale your instrumentation. And then talk about multi-point calibrations too. If you have an instrument, sometimes they can linearize. So you have a particularly nonlinear system, say a mechanical assembly that adds nonlinearity to the measurement. You can calibrate that out by applying loads and having your instrument actually apply a linearization to the data. TEDS is where we store calibration data on a chip, serial number of the load cell, capacity, output, and then certain instruments can read that data and self-scale. So it can be pretty handy if you have a lot of load cells. You can just swap them around at will, and the instruments will just figure out what load cells attached to it. So that's pretty nice. Some other considerations, I think, interface designs in to our load cells to make them perform better are moment compensation, creep, and attention to the effects of eccentric loading. Eccentric load sensitivity is a specification we list in all of our low profile load cells. Typically, if it's not on the spec sheet, a load cell has relatively high eccentric load sensitivity. Our low profile load cells, on the other hand, have very low sensitivity to this. So eccentric load is any kind of load that's not exactly on the load axis. Could be bending, could be a torsion, could be a side load. If you have a compression load and you move it off center, that creates a bending. That's an eccentric load. If you have, say, the load cell installed in a rod and the whole rod wants to bend as you're loading it, that'll apply bending moments. They can be the single biggest error in your system. If you're talking about linearity errors that are, say, 0.02%, you might have a 10% moment error in certain systems. So you really have to take that into consideration. Now, low profiles are very good at eliminating that error, but other types of load cells aren't. Let's see. We actually moment compensate every low profile load cell. It's a labor intensive process where we test, repeat, test again, adjust, test until we pull them into a very tight specification. So we actually load the load cell eccentrically, rotate the load, measure, make adjustments. It's fully traceable, so all the moment adjustment we do on every single one of our low profile load cells are recorded, and you could ask to see it for one of your load cells. We could provide that information. Because we understand these effects and test for them, we can state with certainty that the maximum errors under certain conditions will be not to exceed certain amounts. So this is a table showing different models of load cells and basically the maximum allowable extraneous loads and the maximum error you could be expected to see from those. And you see here the numbers are well down into the 0.1% range, whereas, like I said, some other load cells you could have 5 or 10% effectiveness, so they could be very dramatic impact on your measurement. Because we understand all this, we can also start to look at what are all these loads affecting the load cell and what impact do they have, say, on the longevity or the ability to withstand those loads. I won't get into this in great detail, but if you want to dig in with an application engineer, we can actually look at what your expected loads are, including side load, torque, moment, and really figure out, is this the right load cell, or do we have to go to a bigger load cell to survive it? Temperature compensation is important. Like we talked about earlier, if the temperature is, say, changing during a test, that can affect the zero and the output of the load cell. How much effect? Well, it depends how much temperature is changing and how well the load cell is compensated against that. The errors can be either positive or negative. Good news is they're repeatable from test to test. So sometimes if you have large temperature swings, you can characterize the system, and then you can, say, subtract out the shift if you know what they are. Temperature effect on zero is what happens to the zero signal as you change temperature. So if you have no load on the load cell and change the temperature, the zero is going to move around. You can see that on the left of this chart. You can see that little band as temperature goes up and down. The band actually where zero starts moves up and down as well. But you notice the shape of the output signal stays the same. So the slope of that curve is the same. It just moves up and down. This is one that has relatively high impact on load measurements when you're trying to measure in the low part of the load cell's capacity. So even if you have a very tight temperature spec, if you have a large temperature swing and you're measuring, say, at 5% of the load cell capacity, the errors are based on the whole capacity of the load cell. So it's a 1,000-pound load cell based on 1,000 pounds. So these can have significant impact on low-level measurements because they're a big proportion of what you're trying to measure. Temperature compensation of zero, interface tests at at a cold temperature and a hot temperature. That tends to flatten the temperature curve of the zero out around room temperature, which is desirable because most testing is done around room temperature. So you have, say, 10-degree swing around room temperature, you'll basically see almost no effect. If we know what you're going to be doing, though, say, oh, you're only going to be using it at high temperature, we can actually run the temperature compensation to take that into account. This little chart just basically shows an uncompensated load cell, one that's compensated at only room and hot temperature, and then one that's compensated at both cold and hot. And say the cold-hot compensation flattens it out around room temperature. Temperature spectrum output is a percent of reading, and it's per degree F. That's basically the slope of your output signal changes. So say you have output of 3 millivolts per volt, at room temperature at 100 degrees hotter, it might be 3.1 millivolts per volt. So that's an error. That one is repeatable as well. So sometimes in a temperature, if you know the temperature is going to be 100 degrees hotter, 10 minutes into your test, you can actually cycle your load cell, say with a known load and characterize it, and then you can subtract out, make it like a temperature lookup table. Typically people don't like to do that, so it's better to just have a load cell that's as insensitive as possible to temperature. Interface does that by using our proprietary temperature compensated strain gauges, which really helps reduce the temperature effect on output. You can see some typical specifications on our 1200 series low profiles. We get down to 0.0008% per degree F, which is, say, quite tight. Something like 1100 series is even better at half of that. Creep is interesting. It's an effect where with a known constant load, the output of the load cell changes with time. So if you put a weight on a load cell, say 100-pound weight, and your instrument says 100 pounds, come back an hour later, it may say 101 pounds. That is creep. You can mitigate that by, understanding it, and it's repeatable, and it's a symmetrical effect, and most of it occurs early. It doesn't ever stop, but it tapers off, and it's actually a straight line on semi-log paper, which we're showing here. So for example, if the specification is, say, 0.02% in 20 minutes, you might get 0.02% change in 20 minutes. If that's, you wait an hour, maybe you've only got another 0.02%. So it doesn't continue at the same rate, but it also reverses in the same way as it applied. So if you have, say, a load that's on there for an hour, when you pull the load off, your signal output kind of drops back down immediately, following the same path as it increased, but then it slowly over time come back to where it started. Creep is, sometimes you can ignore it entirely. A lot of times there's not enough time in a measurement to really have any creep error. Other times you imagine like a bucket of water and you want to weigh it and see how much the change in weight is due to evaporation of the water. In that case, creep can be more than what you're trying to measure. So in that case, maybe you pick the bucket up, weigh it, sit it down, wait an hour, pick it back up, sit it down. Now you've taken two measurements. The difference in those two measurements is your loss of water, but yet there's no creep error. Calibration and troubleshooting. I'm not going to go into great detail there. Application engineers can definitely help with troubleshooting. We do know that load cells need to be calibrated. They're all calibrated as they're manufactured. They should be recalibrated either by sending them back or calibrating, say, in situ if you can apply known weights or some other method. We do have some troubleshooting guides and books and white papers available. Like I said, our technical services department is standing by for any questions on troubleshooting. Use cases. There's just a few use cases we put together to sort of demonstrate why you might pick one type of load cell or another. This is a pill press machine. It was important that the load cell had small size so it could fit into the machine. Also had to be able to be cleaned because it's a machine that actually makes pills for human consumption. So you needed a stainless steel sealed load cell that could be cleaned. Needed it small enough to fit into the application. We paired it with one of our handheld indicators. The customer can apply the load and measure it with the load cell and see if it's within certain parameters, and then they can take the system, put it away, and then run the press and be confident that they're getting pills done or manufactured correctly. Here's an application for fatigue rated load cells. It's a medical device where if you're going to be testing it, say for life cycle, you want to high cycle loading the specimen. And so, okay, it's going to be, X amount of cycles at what frequency. And you might say, oh, the load cell is going to wear out. So you need a fatigue rated load cell. Something like this also wanted to be relatively small so it could fit in the test machine, relatively low capacity. So our model SSMF, where the F stands for fatigue rated, was a good choice. Low profile load cells are very good when there may be bending moments or misalignment. This is an application where a customer, say, has a load cell in a machine, and they may have multiple machines with multiple load cells, and sometimes they start having issues. Well, how do you know what the issue is? Well, first thing you might want to do is check the load cell. So this allows the customer to pull the load cell out, put it in line with one of our low profile load cells. So it's pretty insensitive to misalignment. So a system like this may have some bending loads in it or whatever. It doesn't really matter. It'll be fairly impervious to it. Apply a load and see, does the load cell do what you expect it to? If it does, great. Put it back in. Now you got to troubleshoot something else in the system. If the load cell isn't doing what you expected, well, maybe you need to replace the load cell. So a lot of things like this can be done to help troubleshooting and prevent having to send something back to get checked. Facts. Cool. Usually answered or asked questions would be, say, like, why do you make your own strain gauges? I touched on that earlier, but we have full control of the strain gauge, and it's a very key component of a strain gauge based sensor. So by making our own, we control it. Also, we make them special so that they're matched to the load cell material. So every kind of material we use have different load cell strain gauges that are matched, and those allow us to have better temperature performance. We also don't have to have the compensation resistors that other manufacturers use. That makes a simpler circuit and also more reliable. And you can see in that just diagram there, you have a load cell without the compensation resistors, which would be an interface load cell, and say a competitor's load cell would have other resistors that add complexity, also add more failure points. Also, we get a little higher output and faster thermal response because you don't have these resistors changing temperature that may not be bonded well to the metal. What type of temperature testing do you do? Say typically we test from 15 to 115, cold and hot, and we compensate so that the performance is best around room temperature. And if you want something different, ask and we would be glad to provide it. This is a cutaway of a load cell showing a low profile load cell, kind of some of the things that make our load cells unique and allow us to provide the best performance. So to summarize, why interface load cells? High performance, we guarantee our load cells will outperform our competitors. Very high accuracy, we use our own strain gauges. We have industry leading temperature compensation. We moment compensate each low profile, and we have a wide capability of engineering products to order to specification. And that's it. Wonder if anybody has any questions.
Thanks, Keith. We did get a question from Dave. He's asking, is temperature compensation achieved using dummy gauges?
And the answer is no. We do temperature compensation of output by matching the strain gauge to the material. Temperature compensation of 0 is done by adding, say, wire into the circuit that has equal resistance change, or I should say opposite resistance change to the circuit.
Any other questions? Oh, Mitchell's asking about training on torque.
That'll be a different webinar.
We do have an upcoming webinar. When is that, Brian?
Yes, our next one's going to be February 25th. Correct me if I'm wrong, and that's going to be on load pins and shackles. We're going to be focusing on that. It's an emerging market, quite a bit of interest. We do have a few questions rolling in here. Torque, we talked about that. That will be potentially a future one later this year. Brian Martinez is asking if we have our own software to read TEDs. Keith, I believe we have some capability there.
We do. We have a number of things. We have some instruments that can, use the TEDS data. We have some of those instruments that can actually write the TEDS data to the chip. We have some software that, hooks up or attaches to a TEDS chip reader writer. And so like when we program a chip, obviously we have to do that in our factory. We have software and we do have it commercially available for sale.
All right, the questions are rolling in. I know there was one about regularly using a load cell above its capacity. Is that acceptable? And I think that's going to be subjective, Keith, but do you want to handle that?
The answer is no, don't do it. Reserve that for accidents. In practice, we know people do. We can say that they typically work reasonably well above their capacity. The problem is you're eating up into your safety factor, so you don't have any extra headroom for something that goes wrong. Also, it doesn't follow exactly the same calibration curve. So, if you're using, say, a 10K load cell with its 10K calibration, if you're loading it to 12K, you're probably not going to hurt it if you do that occasionally, but you may have higher errors than you would have. If we know ahead of time, we could actually calibrate that load cell to 12,000 pounds. Again, that reduces the safety factor though, so it's not recommended, but we know people do it.
All right, great. There's another question about load cell applications at variable altitudes, and I think that's a great question. We certainly have the ability to handle different pressure scenarios. A lot of our product is sent out vented if necessary to be able to tolerate pressure change without causing any zero shift. So again, if you do have applications where you will have either high pressure requirements or pressure change throughout the test, we certainly have solutions that can accommodate that. Another question I see here with regards to error related to wire gauge versus temperature. So I'm guessing that has to do with cables and how they respond to temperature and how that might influence error. Everything responds to temperature, but I'm not sure offhand. Keith, do you have any insight on that?
Yeah, basically, if you're adding cable to your load cell, so say you have a 10-foot cable and you want to add 100 feet of cable, right? That cable adds resistance. The lower gauge cable is better. You say it's kind of absurd to use gauge 10 cable, but 22 gauge is way better than 28 gauge. So the idea would be to use a thicker cable, and that'll have less resistance impact on the measurement.
All right. There is a question too about creep and whether that's the material itself or the strain gauges. And essentially, it's all the elements in the sensor. Everything mechanical will respond to creep. And thus the goal is to match the creep behavior of the bridge to the creep behavior of the load cell material or the flexure. So yes, creep affects both, but you want the end result to trend in the same direction so that you get minimal error or change in signal as a result of that. Also, I see a question about assuming that all LCs are intrinsically safe. They are intrinsically safe devices, but anytime there's a hazardous location or their intrinsic safety requirements, by all means, please review that with the application engineer. As you can understand, it's one thing to look at just the sensor, but you need to factor in all aspects. And again, given that these are typically working off of 5 volt, 10 volt, you need to look at all aspects. So again, anytime there's intrinsically safe requirements or it is a hazardous location, getting to the specifics of what the requirements are is typically the best way to handle that. IP rating for electrical connections. Keith, you want to handle that? I'm sure it varies quite a bit on our different product. I do know that we have various connectors for extreme conditions, if you can shed some light on that.
Yeah, well, typically the best connection is a welded hermetic connection with, say, a submersible cable. Certain connectors are better than others. Some of them, have O-rings and things we can specify. They're actually undersea connectors that we can specify. We use on some of our load pins and load shackles. They're used underwater. Typical connectors, though, especially in the back shell of the mating connector, might be a leak path. The load cell pictured on the screen, actually, that connector typically wouldn't be great for moisture, and that the back shell of the mating connector isn't super well sealed. But some overmolded, other kinds of connectors can be great. So we do just need to know, again, it's really important to talk about these things as we're specifying what load cell and what cable to use, other than, finding out the hard way later.
Great. Another question coming in with regards to better way to tear a load cell, whether to do it by electronics or mechanical preload. Tearing of the system is typically done through the instrumentation. You would just want to ensure that whatever mechanical tear load you have on the sensor isn't going to impede on your usable capacity range. But as far as the load cell is concerned, really no need to accommodate any sort of mechanical tear. These are linear devices as long as you're staying within the range. But again, on the mechanical preload side, it is important how you preload some of the thread introduction, or excuse me, the attachments, especially for the LPs. As Keith mentioned earlier, it's really important to preload that if you can. That's what we do for best results, so that the load path doesn't change through the threads, which can affect very small amounts of linearity hysteresis. So. Frequency measurement limit, how fast the load cell responds. Another great question. That's obviously going to be a function of the particular mechanical flexure design for that sensor. Each sensor, again, as Keith said early on, is a mechanical spring, if you want to think of it that way. So depending on the stiffness or the deflection characteristics of a load cell, you will have different natural frequency characteristics. That's usually documented on our data sheets, so you can get an idea. But generally, the stiffer the sensor, the better it's going to perform in cyclic applications. Anything to add on that, Keith?
I'd say these load cells are great, hundreds of hertz. You're talking tens of thousands of hertz. They're not. So there's definitely a spot where, very high frequencies, these kind of load cells don't work very well. But most of our typical testing customers who are applying cyclical loads to a test specimen, low profile or strain gauge based load cells work great.
All right, Dylan's got a question which pertains to if you're trying to work up a calculated error or work up an error budget, and you have a mechanical tear load on that system before you start your test, and you tear it and then start your measurement. How would you factor in that initial preload in the system, and how that might impact the error budget?
I think that's an interesting question. It can have some impact. Say something like your temperature effect on 0, you can zero out. If you have a lot of preload, though, it's not, you really can't, because you have to go back to 0 to zero it out. So that, can impact it. So your error budget might say, we zero before every measurement, so therefore there is no temperature effect on 0. If you have a lot of preload, you can't make that assumption, for example.
All right, questions keep coming. This is great. What are the recommended amplifier instrumentation brands? I would say Interface. Keith, what would you respond to that with?
We have a wide variety, and they range from small embeddable amplifiers up to inline, ones where they're DIN rail mounted. We have various different digital outputs available: Ethernet, EtherCAT, Modbus, USB. So we have a fine assortment. I would suggest or recommend that you take a look at what Interface has. Obviously, there are other brands. We won't recommend any of those ones, though.
Well, just like we talked about errors that impact load cells, there's various errors that can impact instrumentation, right? So I think it would be a function of the application, or what are the changes in environment, and of course, resolution. If you're doing a digital type conversion, there's a lot of parameters there. But if you've got certain requirements or certain application details, again, we're standing by to talk through those in particular. This is a good question. We've got one here. What is the most frequent problem when installing a load cell?
I would say one of the problems you might have is mechanical installation issues. We kind of talked about it. It's just like a nut or a bolt, really. So it's just a threaded connection, but there's actually a lot more to it. And so people kind of discount how important it is to make sure you have things aligned properly, that you don't have any parallel load paths, because all of the load has to go through the load cell to make a proper measurement. So if you say you have a plate and the plate's riding on the heads of the screws of the load cell, for example, that's going to shunt the load through the, past the measurement. And so really mechanical installation is kind of people don't put enough weight on how important that is, I should say.
Yeah, I would agree. I think we often see where there's either inadequate torque, let's say, in an assembly, or perhaps too much. Of our lower capacity units, you've got to be careful of the installation torque. So I think it's imperative that if you aren't familiar, please go refer or ask for our installation instructions, at which point we'll have clear guidance in terms of recommended torque values and proper methods there to attach to it. Sometimes it's easy to over torque them. Again, these load cells are designed to see axial loads, and oftentimes people crank on things and you transmit too much torsional load through, and now you've got performance parameters that performance issues that may not show up right away. So cables, do the cables and amplifiers affect the results of load cell calibration? I think that's something you can respond to, Keith. I think there's a lot that go in there, and there's different ways of doing it. So touch back maybe on in situ and system level cal.
Yeah, I would say the answer to that is absolutely they can. They don't necessarily, but they absolutely can have a large impact. So it's important to understand, if you have a, say, change cable length, or you have the instrument at a different temperature and the cables, say, running out of an oven into a room temperature room, all those things affect the measurement. And so the cable considerations, if the temperature of the cable is changing during the test, even if the load cell is at a constant temperature, if the cable is changing temperature, it'll cause the signal to change, and that's not something you want in your measurement. And you can mitigate that by shielding the cable from the sun, or you could have fatter cable, which will have less of an effect on that. Some of these things can be calibrated out. If you have a long cable you add, if you then apply loads to your load cell, it takes into account that longer cable is there. So you can completely calibrate out the effect of the cable length on the signal dropping due to the resistance. So it's good to know. Some sense leads, some instruments use sense to measure the resistance, or not resistance, sorry, the voltage, say, at the load cell. In that case, it's pretty much insensitive to any cable effect. You can change cable lengths or whatever, and it doesn't make any difference.
Yeah, and speaking of cables changing temperature, there's many products out there that if they don't have internal temperature compensation for the buttons like our convex BT does, simply handling the cable can actually then have an impact on the signal, pretty pronounced one. So there's a lot of aspects. We talked a lot on the component level today, but there really needs to be a lot of review from a system level standpoint. Paul's asking for a 10 kN or a 2250 pound force application. Is that too much for a 2,000 pound load cell? Yes. It's above the calibrated range. You can't guarantee performance. Load cells will typically stay pretty linear, 10% over capacity, but there's no guarantee on that. And again, you're starting to exercise the load cell into areas where we'd recommend you stay out. So oftentimes you're better off going with a larger sensor. Pay attention to the actual output. That's one advantage of most of our product, especially in the LP ranges. We offer 4 millivolt per volt output. So you may be thinking that jumping up to a higher capacity is going to sacrifice resolution or sacrifice signal, but you need to look and see how much electrical signal are you getting, because if you're getting if you're comparing a 4 millivolt per volt larger capacity unit to something that may only be 2 millivolt per volt for a lower capacity, you may be just as far ahead, but with significant safe overload on top of that. Another question here: what is the maximum sampling frequency for strain gauge load cells? Again, I think Keith touched on that. It's going to depend somewhat on the model, but hundreds of hertz is certainly adequate. If you start getting close to the natural frequency that's posted on our data sheets, we'd definitely review the application with one of our application engineers. Yeah,
so you can expand that a little further. We have certain people who use load cells, say, for impact testing. Then you might need to sample at 10 kilohertz. Load cell doesn't matter how fast you sample the signal, but load cells can only respond so quick as well. And typically a millisecond response time, is typical. So you're not going to get an instantaneous response from load cell, but it's relatively fast. There are no moving parts, and there's no active circuitry. But typically testing, say you're going to test something till it fails, you might want to sample it a couple thousand hertz. Make sure you capture, that exact point where the system fails or spikes.
Got a good question on creep. I really appreciate these questions coming in, and Keith, I might have to defer to you on this one. But the question is, we showed percent creep on a log scale, and most of our specs are given as a function of the first 20 minutes, right? So how would someone then propagate that out to an hour? Is that pretty much a standard logarithmic formula for that?
It is. It's actually a straight line on semi-log paper. So the graph I showed was just that. And so it's a straight line. But if you look at the x-axis, you can see it's like 10 minutes, 10 hours, 10 days, 10 years. And so it really peters out with time, but it never stops. And then as soon as you take the load off, boom, it comes back pretty much how it started. So most of it comes back in the first 20 minutes or so. Then an hour later, you could basically say it's back to where it started. But yet 10 days later, it's still coming back slowly to where it started.
Yeah, I want to make sure everyone's clear on that. If you do have some concern over creep error that's introduced, and you have the ability to record what that non-zero value is as soon as you release that load, that is an accurate measurement of how much creep error was introduced. And to Keith's earlier comments about it being symmetric, you will see that creep decay symmetrically in terms of how it was introduced. So again, you'll first see that non-zero value. That's the amount of creep error that was introduced in that test. Then you will see that signal decay back to a zero in a similar rate that it was introduced. Another question, how quickly should a load cell be compressed, pounds per minute, and how long should one wait after exercising the load cell before checking zero? Bob, I'm not sure I fully follow on that, but when we exercise our load cells before calibration, it's relatively quick. These are typically done in hydraulic frames, and again, they're automated to where they cycle the load and release in what, Keith? Maybe 30-second cycles. What's the interval roughly on that?
Yeah, it's not necessarily important the timing. It's relatively quick, so there's not a lot of creep introduced, and it's really the magnitude of the exercising, not how long it lasts. So if you load it, say 120% for an hour, that's no better than 10 seconds. But it actually introduced a lot of creep while you wait at that load for an hour. So longer, say, exercising means you have to wait longer for the creep to return.
So if the load is a quick cycle, you could check the zero pretty quick after you do that cycling. Is that accurate?
That's correct. Yeah, it should come right back to zero very quickly.
What is the standard range of application for a standard load cell? That is wide. I think you might be talking, well, I'm not sure I can answer that, Alejandro. It's going to be a function, again, of the environmental requirements, the force requirements, but most of our standard load cells would be good for obviously indoor lab testing, outdoor occasional use. If it's going to see sustained outdoor use or potential rain, moisture, we'd have to then move into either specific option codes for those units or different units altogether. All right, I don't see any other questions right now, and we are right on, oh, maybe there's one more. None. Here we go. Another question from Dylan. With what you said about the non-zero value after removing the load equaling the amount of creep, does that apply to changes due to temperature changes also? That's assuming, so the question is there, would that encompass all error? Of course not. That's assuming all consistent other parameters. If the temperature has changed, then you may need to account for that. Temperature effect on both zero and span, like was mentioned, is something you can characterize. And or if the test for it, you might be able to re-zero it before you do your testing. If there is a hot test or a cold test, let's say, and the temperature test is consistent, well, then you can take it up to temperature, tear your system, and then start. And then at that point, you theoretically will not have any influence due to temperature changes at that point. Again, that non-zero return that I shared with regards to creep, that would just be a way to check the creep influence, again, assuming everything else is static. So, all right, Jamie, I think you posted in there that we're going to have this video available online. And again, we encourage you all to sign up for our February webinar. These are getting quite popular, and I don't want to caution people, but the earlier you get signed up, the better. Well, we might hit a limit one day. So,
Yeah,
Jamie,
definitely.
anything you'd like to add?
No, thank you for everyone attending. These were great questions. We will follow up with everyone and give you a link to where we'll be posting this on our YouTube channel. We'll also have it online on our website. If you have specific questions, obviously you can see our team is very well versed in these types of applications, use cases, and technical details that may be important to your next test or which load cell you want to choose. So be sure to reach back to us. We're here to help you in getting the right load cell for your project. So with that, thank you everyone. Again, we'll follow up. The recording will be there, and join us for load pins next month. It'll be exciting.
Thank you, everybody.
Thanks, Keith.
Thanks, everyone.